A very warm welcome to everyone present here. I take this opportunity to introduce our speaker for the day, Mr. Vaibhav Adhikar. He is an applications engineer at ComSol. He has received his master's degree in RF and microwave engineering from the Indian Institute of Space Science and Technology, Trivandrum, and interned at the Semiconductor Laboratory, ISRO, Chandigarh, designing flexible antennas and passive devices using silicon micromachining for THZ communications. With his expertise, you'll gain valuable knowledge from his real world experience. So, I welcome you.
Thank you. Thanks for the introduction. Uh, yes. So, shall we start the presentation or we are still waiting?
Yes, so we can start.
Yeah, thanks. Thanks for the confirmation. Okay. Uh, so, good afternoon, all. Uh, as Shazib introduced me, I'm Vaibhav Adhikar, working as application engineer, and I extend my warm appreciation to everyone participating in this webinar on multiphysics modeling. As we are well aware, future mobile networks, which consist of Internet of Things, Internet of Space, and Internet of Everything, revolves around rapid communication. Given the immense data size that needs to be addressed without lag, it is critical that we ensure wide bandwidth for our communication system. To meet these high data rate communication demands, millimeter waves, millimeter wave based communication technology are emerging as a promising solution. As the complexity of design, manufacturing, and testing are escalating, the necessity to grow for the realistic simulating physical phenomena through numerical modeling. In our discussion today, we will explore effectiveness of simulation method and ways to extract physical physical phenomena beyond the conventional electromagnetics. Today, it is it's a reality that consumer electronic devices comes with wireless capabilities, making it evident that we are residing in the era of IoT. The goal is to achieve low latency and superior communication quality, especially when we are handling enormous volume of information, which necessitates the high data rate communication. The ultimate aim is to ensure seamless high-speed communication accommodating an abundance of signal simultaneously implies that need for broader bandwidth for high-speed data transmission. Hence, we are watching upsurge in the system bus frequency and even the carrier operating frequency. As a result, we are, we are gradually transitioning from conventional microwave to millimeter wave, known for its short wavelength. While the smaller electrical length allows for more compact and lighter devices, it also results into the path loss. This requires high gain antennas to compensate these losses. Further, the system becomes more susceptible to physical distortion due to the environmental shifts such as extreme temperature or extreme humidity levels. Therefore, the need for numerical models to anticipate and capture all the possible physical phenomena is increasing. And as this would enhance the efficiency of the developing cycle by reducing the need for repetitive prototyping and fabrication and testing processes. For instance, see this Ka band 20 gigahertz of antenna array position underneath the capacitive touch sensor electrodes, which might be function as a Faraday's cage and can obstructing the radiation. But the design characteristics of touch sensor composed of dielectric and the electrodes arranged orthogonally, allowing for some particular frequency it will transmit. By, re- by redesigning this grid, it we, we can we can design the frequency selective surface that is permeable to specific millimeter band. These modified electrodes set up via periodic unit cell simulation at the initial stage and offering room for improvement, including less than 5 dB, zero point 0.5 dB of insertion loss and better than 10, 10 dB of reflectivity for the entire 5G millimeter band from 26.5 gigahertz to 29.5 gigahertz. Initially, replacing the old electrodes did not lead to expected performance. However, after repositioning the antenna array to maintain the enough distance between the touch sensor and between the antenna, there was 0.7 dB reduction in the realized gain. There was initial apprehension that new design might negatively impact the touch sensor performance. However, it actually improved the sensitivity of the vertical electrodes, allowing for better location and detection via mutual capacitance computation. The scope of the high frequency electromagnetics can extend beyond just compact electronics. Think about the well discussed topic of autonomous vehicle. These vehicles may employ K band or W band automotive radar to identify and range the nearby objects. For example, they will use the series fed microstrip patch antenna arrays. All vehicles remain interconnected, communicating to determine the most efficient route and create the most effective traffic flow, which entails processing the enormous volume of data. This opens the possibility of utilizing the millimeter wave mobile network platform, which is already existed. Once the electronic components are installed in a vehicle, it is also essential to evaluate their performance on their effects on the other part as well, considering the aspects like interference and the compatibility. These assessments can virtually conducted, of course, by means of the simulation tools. Now, let us broaden our view of high-speed communication, moving from tiny electronic device to something significantly large, like the cosmos. Indeed, we are talking about the satellite communication, a technology capable of enabling long distance transmission by bouncing the signal by bouncing the signals from one satellite to another satellite. We have witnessed in attempts to establish a global internet service by deploying numerous satellites into the low Earth orbit. What particularly excites me about the space exploration is the sight of this Perseverance landing on the Mars was quite thrilling. I certainly felt that a surge, certainly felt a surge of enthusiasm. It inspired me to begin crafting a reverse engineered simulation uh, to model the antenna array. I derived the specification from NASA's web page, which provides the detail about the size, operating frequency, and the gain measurement. The enclosure shape in the visible image gave me an insight about the grid configuration and number of array elements. My model utilizes a probe-fed circularly polarized microstrip patch antenna, achieving about 24 dBi gain. minus 70 dB of the first side lobe level and 1 dB bore side axial ratio. The elements are arranged in a triangular grid, which compared to the if you compare to the traditional rectangular grid, results in a very lower side lobe level. Moreover, the main beam is wider, allowing for expanded coverage area without sacrificing the signal quality. The traditional satellite communication system offers a means of tracking satellite data. This typically this typically achieved using high gain antennas with sharply defined radiation pattern. Since we are depicting all these figures in a dB scale, a pattern might not be seems incredibly sharp. Different plotting dynamic range can create variety of interpretation. So it's important to consider the plot range when visualizing or any or assessing the radiation performance of your antenna. Then what sort of tangible components can be represented using these numerical models? They could consist of commercial off-the-shelf antennas as well. It's noteworthy that devices need not to be radiating. They could be employed to contain a signal through process of dividing, combining, or even coupling. Alternatively, they could be selectively focused on a particular band to filter or block the other signals. There exists a simulation model that are specifically designed to observe these physical effects. Regardless of what these models represent, we typically verify the S parameters or field intensity to be sure about the susceptibility of the device and to extend the unwanted noise that could be generated. Within the electromagnetic simulation model, it is also possible to incorporate the factors such as the thermal drift effect, structural distortion, which can alter frequency predictions. Certainly, devices as these we have discussed, all can be modeled using the popular multiphysics, a comprehensive software tools that enables the realization of multiphysics
It
simulation.
is not audible properly. Hello, sir. It is not audible properly.
Sorry. Other are also facing the same. Hello,
Yeah, echo sound is coming.
hello.
Your voice is hello, sir. Your voice is not clear.
Okay. So any part that you would like to repeat, uh, or shall I proceed from here?
கனெக்ட் ஆயிடுச்சுல. என்ன வெறும் இதுதான் இருக்கு. கிளாஸ் போலாமா? கேட்குமா? அத்தையும் கேட்டுதான் அடிக்குது. அப்ப நீங்க
Yes, you can go ahead. Yes, so now,
Whatever, sir.
yeah. Hello.
Yes, sir. You can go ahead, sir. Whatever, sir.
Okay, thanks. Uh, okay, so all the in the previous slide I discussed about various devices that can be modeled with the electromagnetic simulation. And certainly, these devices can be modeled using console multiphysics, a comprehensive software suites that enables the realization of multiphysics simulation. It spans everything from geometry creation to result analysis, offering a streamlined modeling workflow. You can even transform your simulation model into user-friendly apps featuring more intuitive and tailored graphical user interface. These apps can be shared with peers or clients via web browser or standalone executable files. That does not necessitate the additional software license purchase to run these apps. Let's take a closer look at the console desktop. We present we present a clear uh, we present a clean, user-friendly interface where all modeling steps are logged and can be amended later if required. This primarily takes place into the model builder window. We enter or choose our custom setting into the adjacent window, and then visualize the result into the graphics window. The top horizontal menu here can is housed for the most crucial option, saving you from having to remember the location of specific boundary condition. Alternatively, you can simply right click here on the physics and uh, Abdul Rahman, I will request you to mute yourself at your end. Yes. So alternatively, you can simply right click on the physics, or you can uh, by right click, all the relevant options will start appear into the context menu. With console, we offer an wide range of tailored software to address the electromagnetic phenomena. Indeed, we boost a strong portfolio for the electromagnetic simulation, covering low frequency to high frequency, and at a times providing faster, more efficient solution via asymptotic methods. Now, when we are discussing this millimeter wave or sub terahertz, uh, sorry, sub terahertz, sub terahertz for the next generation mobile network, which which product should we opt for? Regardless of the frequency, here we are solving for the Maxwell's wave equation when running the full wave simulation. However, each module is specialized to offer an enhanced modeling environment for specific application. For millimeter wave simulation, the RF module is well suited and should be like frequency wise. The wave optics module also address the millimeter wave band, but the choice depends on your preference. You may prefer to default setting in the RF module, where you specify the material properties with the permittivity, permeability, and conductivity, along with the electrical circuits and the lump component approximation, analyzing the S parameter response. Or alternatively, you if you are an optical scholar, you might prefer the configuring your model with the refractive index, studying the reflectance, transmittance, which can be extended to the large optical structure using the beam envelope method that is available with the wave optics module. Now question arises, how would we make simulation model using these modules? For instance, with the RF module. Well, the RF module is, is high frequency electromagnetic simulation tool designed to address various electromagnetic phenomena by combining different physics interface and study steps. It is crafted specifically for design engineer focusing on microwave, millimeter wave, or even terahertz application, facilitating for the modeling of components such as the antennas, waveguides, filters, passive circuits, metamaterials, or even the frequency selective surface. It employs the finite element method to calculate the power dissipation. Electromagnetics modeling isn't restricted to frequency domain, but it is also possible to consider the time domain analysis. The transient interface is add-on for studying the nonlinear electromagnetic wave behavior and time domain reflectometry analysis. Further, the asymptotic interface will allow for a quick estimation of the radar cross-section of a convex type scatterer. Additionally, when, when the coupling between the adjacent transmission line is minimal, the transmission line interface can also save significant time and resources. This interface uses the transmission line equation to solve the simulation that typically takes several minutes to hour within just seconds. You would have also opportunity to maximize your computational resources by merging two distinct numerical methods, that is the finite element method and the boundary element method. This combination allows you a precise modeling of the sub-wavelength using FEM with the results of bidirectionally coupled with the boundary element method. This way, the wave propagation in a free space beyond the uh, traditional simulation domain limit we, we can also observe. This provides insights into the effect of large platforms where FEM devices is located. Real world scenario cannot be fully captured by single physics domain as we live in a multi-physics world. Hence, all equation in console simulation models are fully coupled, allowing electromagnetic fields to influence and can be affected by other physics. This capacity for multiphysics study extends the simulation capabilities beyond the traditional single physics analysis. For instance, see the combination of electromagnetics with the heat transfer. The equations are fully coupled, enabling the interplay between the electromagnetic fields and other physics domain. By solving the Maxwell's wave equation in the frequency domain and heat transfer equation either into the stationary or time domain simultaneously, we can calculate the temperature variation over a time and effects of changing the material properties due to these temperature shifts. Traditional electromagnetic analysis can be further enhanced to include the structural deformation, which alters the resonating behavior of your testing devices. Multiphysics simulation effectively captures the millimeter wave circuit performance under the realistic operating conditions, thereby eliminating the need for expensive and time-consuming environmental tests. Through simulation, the number of iterations in development cycle is reduced, and it can fast tracks the design and fabrication and testing process. In simulation software, the actual world is represented by numerical expression known as the boundary condition. Consider a semi-anechoic chamber with a biconical antennas linked to a network analyzer. This, this connection can be symbolized by a lump port. The absorbers on the side walls and the ceilings can be mimicked with the infinite half upper space, minimizing the reflection, which can be represented by absorbing boundary condition. If simulation structure is repetitive, it isn't really necessary to include all the elements. For example, a walls of absorber could be simplified a single pyramidal unit cell with a periodic condition. Here you can see a virtual EMI/EMC testing environments for environment setup for the vehicles. Delving into the specific, the lump ports and port features are used to excite and terminate transmission line. These connections, these connections are basically to the network analyzer, signal generators, or spectrum analyzer, or it could be match loads, or termination with the custom impedances. This boundary condition provides information about the reflection, transmission, and similar to measuring the S parameters into the lab, and can cater a wide range of cable types, including waveguides, microstrip lines, and all other applications. Different type of ports can be utilized for various applications. A user-defined type of port allows for the manual definition. Rectangular or circular type of ports are suitable for exciting or terminating the ends of metallic waveguides that could be rectangular or circular. The coaxial type of ports can be used even when the characteristic impedance is not known on the end of the coaxial cable connector, or for the match mode setup. For arbitrary, if you are dealing with the arbitrary shaped waveguides and materials, the numeric type of ports can find the port modes that you need. In the periodic unit cell, of course, the periodic type of port can be used. When testing these radiating components, it is essential to prevent performance distortion by components' own radiating fields. Ideally, an infinite space with no obstacle is preferred, often simulated in a fully anechoic chamber. Pyramidal absorber can be replicated in such a room, but they are computationally demanding. The perfectly matched layer is the most efficient way to represent them, and the numerical representation can be even simpler with a scattering boundary condition. Metal is, of course, a key material for a high frequency electronics, and it is often used to fabricate the transmission lines which are carrying the signals. The, there are various ways to represent your metallic objects depending on the expected losses and the desired accuracy. If losses are negligible, a lossless, perfectly electrical conductor, that is PEC, can be used. If it is a lossy thin layer, you can simplify this thin conformal layer to a 2D plane and then apply a transition boundary condition. For a lossy volume where wave doesn't penetrate due to the thickness, use the impedance boundary condition. For a traditional microwave application, PEC might be a sufficient. However, for higher frequencies like terahertz, addressing the losses becomes important. Periodic condition is a versatile tool, particularly useful when designing the metamaterials or modeling the plasmonic grating applications. A Floquet periodicity, one of the several types, can handle a wave incident at any arbitrary angle. When the main polarization is known, symmetric condition such as the PEC or PMC can be used. This software contains many more boundary conditions and advanced functionality. What I have outlined here are just the basic ones, but they are sufficient to model a typical antennas and circuits. You might be wondering how to begin this applying these boundary conditions. The RF module offers over 100 and thousands of examples for modeling with detailed step-by-step instructions. This guide will help you to construct the geometry, apply the boundary condition, and display the results with the impressive visualization effects. This application range from the antennas, couplers, ferromagnetic devices, scattering radar cross-section calculations, and various transmission lines. So let's put this basic boundary condition to, to model an antenna array. We will present here a two antenna array model. One is the conventional antenna array, where you will observe both 3D model and a simplified version, complemented by widely recognized antenna array factor. So let me go to the console environment. So here you can see a 8 by 4 antenna array has been modeled. The patch antenna model geometry is coming from the geometry parts. This geometry part is nothing but the customized, fully parameterized geometry. Here, a user-defined geometry part I have built, and in the latter stage, I have used, I have multiplied with the help of array feature. I have multiplied this into 8 by 4 antenna array. I consider the block for the surrounding air environment. Next step is to assign the material properties. The surrounding of this antenna is nothing but the air. This is the planar antenna array into the XY plane, and the substrate here I have defined with the material permittivity, relative permittivity as a 3.38 and relative permeability as a 1. And I consider electrical conductivity as a 0. That is the ideal scenario. Under the physics set, here you can see each antenna element is applied with the voltage excitation, and this voltage excitation is is having the phase difference. This phase difference corresponding to the cos phi, which basically which basically will steer the antenna main radiation lobe into the into the uh, out of plane of this antenna. So here you can see the progressive phase shift that we have applied. The perfect electrical conductor has been applied to the ground, and perfect electrical conductor is considered for the microstrip patch. After performing the mission, we we solve the study one. Here we perform the parametric sweep for the phase, the progressive phase, that is pi by 2 and pi by 3, to steer the antenna radiation. I run this simulation for the F naught frequency, and that F naught frequency is basically defined here under the parameters. That is 1.575 of gigahertz. This simulation, you can see, has took almost 5 minutes and 40 seconds to compute. And after successful computation, we have got the results. So here you can see a 3D electric field distribution. The far field radiation pattern into the 2D, and that too for each phi. So when phi was pi by 2, nothing but the 1.57. So here you can see the main lobe was around the 90-degree. If I visualize the evaluation plane, it is the this plane is nothing but the perpendicular to the plane of our geometry. This plane is nothing but the perpendicular to the plane of our geometry, which is nothing but in xy plane. And we are plotting the far field electric into the dB form. For the phi equal to pi by 3, again the main lobe is basically get steered into the 60-degree. So is there any simplest way where we can reduce our computational time? So answer is of course yes. So let us, and how we can simulate this antenna array structure. So let us go to the modeling environment, and let me start with the 3D space environment, as this antenna is nothing but the 3D. Here software will ask me to select the physics interface. So let me select the physics interface as the electromagnetic wave frequency domain. Let me click on add. The next step is to add study. I'm going to perform the frequency domain study, and let me click on done. To save the time, let me insert the geometry sequence from the previous model. Here we are going to only use a unit cell of this 8 by 4 antenna array structure. As you can see, a unit cell patch I have designed, and surrounding to it the block, uh, a air block I have designed. The next step is to, of course, assign the material properties. So let me add the material from the built-in section. Air, I will add, let's say, all material. If the material properties that you are interested is not available into the material library, in that case, you can definitely create your own material with the help of blank material option. So let me select this blank material for the substrate. You can also visualize selections by clicking on wireframe rendering. And the material properties here is nothing but the 3.38 relative permeability as a 1 and electrical conductivity as a 0. Now we are ready with the material properties. The next step here we are going to perform in order to consider the infinite array structure. We are going to consider the periodic boundary condition on the side walls. And here we are going to uh, we are going to choose we are going to choose the blockade type of periodicity, and this periodicity will basically uh, basically take care the progressive phase difference. So let me add the periodic condition first of all, and that is nothing but by if I right click on physics interface, and here you can see a periodic type of a periodic condition is available for the air as well as the substrate. I have selected in the x direction. I would like to have phase difference, and that I can consider by applying the by using the flow-kit type of periodicity. And here, let me use the wave vector EMW A naught predefined variable multiplied with the cos phi. So here I can choose, let's say, a parameter I need to define, let's say phi, and it is nothing but the pi by 2 radii. This type of periodicity I have applied EMW A naught. Then next step is to apply the periodic condition into the xz plane. Into the xz plane, I can consider as a continuity type of periodicity where the electric field distribution will be copied from source to destination boundary as it is. The next step is to provide the excitation. And for that, I can use the Lamport boundary condition. I can excite this insect fed patch antenna with uniform voltage. And let me add the perfect electrical conductor as a boundary condition for my patch. And by default, all the external boundaries are uh, uh, basically the perfect electrical conductor. So I can skip. Then next part is to consider I'm interested in performing the far field analysis of this antenna. So let me add the far field domain here. I would like to perform this far field domain analysis only into the air environment. So let me select far field domain corresponding to air only. The next part is, so as here you can see, the perfect electrical conductor is also applied to the top boundary, which will reflect the electromagnetic radiation and can alter the performance of this antenna. So we don't want that. And we can absorb this electromagnetic radiation by considering the scattering boundary condition. Now we are set up with the physics. The next part is the here I am going to perform this analysis for 1.75 1.575 gigahertz. You can also visualize the mesh. Some of the boundaries I can also hide so that you can visualize the mesh inside. And this meshing looks fine for me. To save the time, I also have the solved version of this model. So let me open this model. So here you can see I have the solved version. I applied the Lamport excitation, the perfect electrical conductor, periodic condition into the x direction, periodic condition into the y direction, scattering boundary condition for the top boundary, which is here hidden. I reset the red option, and far field domain is applied to domain number 2. And we solve the study 2 with a parametric sweep for the phi variable for pi by 2 and pi by 3 for the single frequency. And now you can see only in the 30 seconds we have got the results. Now here, if you compare the 2D far field response, this is the full array, full 3D array response is represented into dash form, and periodic model is represented with the solid lines. And you can see there is pretty much for the main lobe at least, you can see uh, a good matching between the 3D model and the 2D model. One thing, of course, here is to note that the far field node that we have added here is only considered for the unit cell. And if I multiply this unit cell response with the well-known array factor, then only I will get the array antenna array radiation pattern for this periodic structure. And that is what has been done here in this expression. Let me expand this expression. So here we are mentioning, I would like to multiply the far field, let's say the electric field distribution uh, with, with the array factor, but into the log scale. This multiplication will become addition. And here, for this is the predefined function available with the COMSOL multiphysics, that is EMW array factor AF3, 3 stands for 3D structure. And we are considering 8 by 4 by 1 array and having the phase difference of 0, uh, sorry, 0.48, 0.48 and 0, the space dimension, the separation between them, and the phase of variation into the x direction, nothing but the 2 minus 2 pi 0.48 cos phi into the x, into the y direction 0, into the z direction again 0. And thus we have compared the radiation pattern with the full array simulation. So here you can see only the a 3D far field pattern representing only the single antenna response, but that this array this far field radiation pattern we have multiplied with the array factor. Here you can see the gain comparison for the periodic model. You can see a good this. So here you can see the full full array model and the periodic model. The main law is exactly matching. But this far field radiation pattern become noisy when we are going towards the side lobe level. This is because again we have considered the far field domain only for the single unit cell. So of course, this is the trade-off that we need to address. If you would like to have faster response, definitely you can go with such a uh, such a approach, and you can at least intuitively find the radiation pattern for your antenna array structure. I hope this demonstration was helpful for you. And let me go back to my presentation. So there are again numerous valuable resources available at the COMSOL website. This slide basically shows the selection of these that could be like blog posts, videos, user story, models and application. All these resources are incredibly useful. If I had to choose one, I would say uh, I will go with the application gallery at most. It includes over thousands different examples, so I can always find a something relevant to what I'm trying to simulate and I can learn from it. Indeed, the application gallery offers tutorial example model uh, as well as the detailed instructions. Even without console, you can access and download this documentation, which will allow you to learn about this modeling workflow, as well as you can design the principle and have the motivation that guides the creation of all these models. If I browse you through the website, once you come to the console web page, here into the bottom, all these resources you can find blogs, learning centers, the physics-wise classification has been done here. So that definitely you can work. And this is what I was talking about, the model and application file. So here you can, more than thousands of examples are available. And, and all of these examples comes with the model file, that is .mph file, and the instruction, the PDF instruction file, so that you can you can learn from this. You can have access to the introduction and how to build this model from scratch. Introduction is present, the notes about the console implementation, and the step-by-step instruction to build this model from scratch to get these results. With this, I have concluded my presentation. If you have any question, please feel free to ask.
Excuse me, sir.
Yes.
Sir, the simulation have shown it is also possible using HFSS and CST. So why should we use console?
Okay. So so that again lies into the application that you are revolving around. Let's say you would like not only perform the electromagnetic analysis, but also you would like to consider the multiple physics effect, such as the structural deformation into your electromagnetic structure, or could be the Could be you would like to consider the temperature effects. Many a times, the material properties are itself temperature dependent. So you would like to monitor this temperature rise, let's say, uh, simultaneously while working with the heat transfer physics as well as working with the electromagnetic physics. So COMSOL multiphysics is a tool where you can perform all the physics, you can consider all the physics under the single GUI. And the interesting part here is the predefined modeling, predefined coupling between these physics interface is already available. One such example here I would like to talk here is related to RF heating. So if I go to the RF heating, here you can see we are not only dealing with the RF phenomena, but also the heating effect. And simultaneously, all this effect has been considered into the single model itself. So I hope I was able to answer your query.
Yes, sir. Sir, I have another question. Can you derive circuit model from in this using this software?
You would like to draw a circuit model or you would like to extract the circuit, lump circuit modeling?
Is it possible to extract circuit model?
Yes, up to some extent. So there is one uh, add-in basically available, uh, and that discussion, let me, so, extraction, that feature is basically available with the AC/DC module. So here you can see extracting the electrical circuit from the electromagnetic simulation. So this discussion has been done here. I would highly recommend you to visit this blog. From here, if I have the PCB design, how I can extract the lump equivalent circuit out of it. So that discussion has been done here. So this might be a good starting point for your analysis. Let me share this into the chat box as well. Yes. So this is the block I was talking about. Okay, I think my screen was paused. So yes, so here you can see extracting the electrical circuit from the electromagnetic simulation. This block I was talking about. And before this, I was talking about the electromagnetic heating block. This is this block I was talking, modeling the RF and microwave heating. Yes. Please do let me know if you have any further questions. Yes. So with this, I have concluded my session. If you have any further questions, please do reach out to us at support@console.com. I'm also sharing this email address with all of you. Okay, I think there were questions in the chat box also. Think I missed this part. Bhagwati was asking the transmittance, reflectance, which module should I use? So I think in my discussion itself, by default, with the help of wave optics module, you will get the transmittance, reflectance graph. But again, with the RF module also, you will have by default plots for the S parameter response. And by applying the standard conversion, you can also convert the S parameter values into the transmittance and reflectance. So thank you, uh, all of you, uh, and have a good day.